Here's a quick overview of the story of how to identify polynomials. I'm running a risk of recording this right now because I can see out my window from my chair here, and just a few minutes ago the mail truck went up the other side of the street, which means in a few minutes it's going to turn around and come back down my side of the street, which means the dogs are going to start barking. Probably. We'll see. So, polynomials. Why do you have to be able to identify polynomials specifically? I mean, functions are functions, right? Who cares what subtype of functions that you have? Well, if you think of functions as animals in a zoo, sure, all the animals or the hoofed animals are put together, but even still, it's a good idea sometimes to be able to tell a zebra apart from an antelope. So yeah, functions are functions in general, and there's only so much use to subdivide them into types, but there's actually a lot of use to subdivide them into types, and it is useful to be able to identify what polynomials are specifically. So just real quickly, the idea of a function in general: a function is like a mathematical vending machine where you plug in coins or numbers into the coin slot. But the thing with functions, unlike a vending machine, is that there might be multiple coin slots. So the variable x is the coin, but you might have to put it in several different places. Okay? And then the food that you get back from this mathematical vending machine is going to taste differently depending on what happens to the coins when you put them in. Okay? In other words, here we have a function named f. Its variable is identified as x, which means x marks the spot, or the vending machine analogy, x is the coin slot where we're going to put in a number. And here we have to pick a number and put it in twice because we see 3x squared. That's one term in this polynomial. Then minus 2x, it's another term in this polynomial. And so we have to put our coin in twice, or our number in twice. And then the flavor that we get, the number that comes back, depends on what happens to those x's. So here, one of them is squared and then multiplied by 3. The other one is multiplied by -2. Then we add those two things together and also add a 5. So if we plug in x equals 1, we get 3 minus 2 plus 5, 6. Okay? Now, if we take that exact same structure of the function and slap a square root over it, this is not a polynomial anymore. Sure, it has a polynomial in it, but the thing as a whole is no longer a polynomial. And so we're going to talk about how to tell these things apart. Now, I just told you this is a polynomial, 3x squared minus 2x plus 5. Well, why? What's special about this thing that makes it a polynomial? Well, if you look at the terms, you'll notice that the instances of x are all raised to integer powers of 2, 1, and 0 in order. In this middle term, the minus 2x, remember there's a ghost exponent of 1 on that x. X to the first, same thing. So there is an exponent of 1, even though it's hiding like a ghost. And then on that 5 term, well, there's still a ghost in that term because 5 is 5 times 1. And you may remember that a number raised to the 0 power is always 1. 2 to the 0, 1. 7.7 to the 0, 1. Pi squared over the square root of 19 raised to the 0, 1. Okay, so 5 times 1 is the same thing as 5 times x to the 0. So we could flesh this polynomial out and maybe fill in that ghost of x to the 0 on the last term, the 5. There's still that ghost of 1 exponent on the middle term, but generally speaking, we don't need to do that because we know what's there even if we don't see it visibly. So, it's not worth the trouble. So generally you have a polynomial when you look at your function, and every time you spot that variable, it's raised to a non-negative integer power. And we say non-negative instead of positive because we need to include 0. Okay, x or y or t or q or whatever the variable is cannot be raised to the 1/2. It cannot be raised to the -2.7. right? None of that business. It can only be raised to non-negative integer powers, and the terms that contain those instances of the variable raised to the right power have to be alone. They can be multiplied by a constant, that's fine, but they can't be like multiplied by a second term that wouldn't produce another term that's raised to an integer power. Okay, so every time you see the variable, at worst it's multiplied by a constant. I guess that line I just put in basically repeats the first one. It can't be raised to anything other than a non-negative integer power. And there can't be any other nonsense. You can't throw in a trig function. You can't multiply two terms together. You can't slap a square root over the whole thing like I did on the previous example. None of that. None of that. So here is the general structure of a polynomial. This is quite a bowl of alphabet soup, okay, but it tells a story. This shows us that there are a bunch of instances of the variable x. However, at worst, in each term that's added to other stuff, the worst thing that happens to that x is it's raised to a non-negative exponent and it's multiplied by a constant, right? The resulting of the raising that variable to the exponent is then multiplied by a constant. Okay, so the a's, the a sub 0, a sub 1, a sub 2, those are called coefficients. Those are just the numbers that multiply the instances of x or x squared or x cubed or whatever it is. And we number them so that the counting of them, a0, a1, a2, is consistent with the exponent that's on the x that constant is stuck to. So a1 is the coefficient of x to the first, a2 is the coefficient of x squared, a0 is that floating constant, which technically speaking is a0 times x to the 0. Okay, those are coefficients. Wherever you see the term that gives you the highest power of x that's present in the function, that high power is the degree of the polynomial. And the coefficient, or the constant, that's stuck to the term that you just used to identify the degree is called the leading coefficient. Now, this is not about which is first in line from left to right. It's about the coefficient that's attached to the term that gave you the degree of the polynomial. It's where you found the highest power of x. So the polynomial we already looked at, 3x squared minus 2x plus 5. This is as garden variety a polynomial as it's going to get. The exponents are decreasing from left to right. The degree is 2. That's not very exciting. Because the x squared term is the one we looked at to get that degree, the multiple of that x squared is the leading coefficient, so 3. And those two identifiers stay the same whether or not we scramble up the terms and write the function in a different order. Because function-wise, 3x squared minus 2x plus 5 is the same thing as minus 2x plus 3x squared plus 5. We are just using, remember the buzzword, the commutative property of addition, that you can change the order around, right? The terms can commute. So when things are added together, just scrambling the order doesn't ruin anything. So 3x squared minus 2x plus 5, same function as negative 2x plus 3x squared plus 5, same function as 5 minus 2x plus 3x squared. They're all the same polynomial. The degree of every one of them is 2, and the leading coefficient is 3. Now I highlighted the middle one, the negative 2x plus 3x squared plus 5 in blue, just to emphasize that if the polynomial is presented this way, the leading coefficient is not suddenly negative 2. Okay, it's first in line from left to right the way that the polynomial is presented, but that's not the coefficient that's stuck to the term that locates the degree. That degree is the 3x is coming from the 3x squared term. X squared, 2 is the highest power of x, so the degree of this polynomial is 2, and that term then also assigns the leading coefficient as 3. So again, it's not left to right, it's wherever you looked to get the degree. Okay, here are two just simple examples of polynomials. Here, this one's written with decreasing exponent from left to right. That makes us happy. The degree of this one is 5. The leading coefficient is 6. Okay. This one, ooh, it's got t's in it. Well, who cares? It's still a variable. Just because it's not x, that doesn't matter. So let's go look for where the variable t is raised to the highest power. Looks like it's now the last term. That's the 4t cubed. So the degree of this polynomial is 3, and the leading coefficient is 4. And now let's practice, what's a polynomial, what isn't. F of x equals 12. It is a polynomial. It's like the easiest polynomial you can get. A constant is a polynomial because 12 is the same thing as 12 times x to the 0. Right? So that fits the definition of a polynomial. G of x equals 3x plus 12. Polynomial. Degree 1, leading coefficient 3. You may recognize this otherwise as the equation of a line. Toss a square root over that 3x plus 12. Now it's no longer a polynomial. Here's one. I've switched the variable from x to t and also named it s, but again, that's cosmetics. That doesn't matter. Square root of t to the 4th plus 16. So wouldn't that be t squared plus 4? Because the square root of t to the 4th is t squared, and the square root of 16 is 4. So that should be a polynomial, right? No. You cannot do the square root of the first term plus the square root of the second term. The square root doesn't break apart the plus at the plus sign and separate into 2 square roots. It doesn't work like that. So this is what it is. It doesn't simplify any further. It is not a polynomial. This one here, no, not a polynomial because of that exponent of 3.25. That spoils it. Okay, and then here's a bonus question just for something that's really subtle. Now, if you're not ready for something really subtle, just close the video now and go on about your day. But is this a polynomial? Because, think about this. That numerator, x squared minus, well, the function is x squared minus 1 over x minus 1. That numerator factors into x plus 1 times x minus 1. And then those x minus 1 terms cancel. So this function simplifies to x plus 1. So it's a polynomial of degree 1, right? Wrong. Okay? This is the subtle thing. As soon as this function is presented as x squared minus 1 over x minus 1, from that instant forward, no matter what happens to that function cosmetically, we are not allowed to use x equals 1 anymore because of that denominator. Yes, it simplifies algebraically to x plus 1, but in the back of our minds, we look at that x plus 1 and we say, well, this function is equal to x plus 1, except I'm still not allowed to use x equals 1. And so the graph of this function is a straight line, but there's a hole in it right there at x equals 1, because we cannot assign that point. And so this thing's pretty darn close to perhaps being a polynomial when it's simplified, but it is not because of that hole in the graph that we get there at x equals 1. And that's the fun stuff. All right, so there is a review of polynomials, and the dogs never barked.